Hi, we now continue with the discussion of classic clustering methods, and in this lecture we look at hierarchical clustering. And I'm going to start by explaining the principle, which actually is very straightforward, and then focus on the linkage functions, the linkage options, which are really the way that we conceptualize of distance between clusters. Distance between observations is straightforward. We can use Euclidean distance, Manhattan distance, or whichever distance measure, but distance between clusters means that we somehow have to summarize how the different observations in one cluster relate to the different observations in another cluster, and that's embedded in the linkage option. And then I'll show some repercussions of this choice. As before, sensitivity analysis will be very important. Okay, the principle of hierarchical clustering, and in particular, in this lecture, I'll talk about agglomerative clustering, which is the bottom-up procedure, as opposed to divisive clustering, which is a top-down approach. And we'll see some examples of the divisive hierarchical clustering when we discuss spatially constrained clustering a little later. So it's a bottom-up approach. Initially, we have n clusters, if n is the number of observations, and every observation is its own cluster. And so if you think about it, what is the within sum of squares? It's 0, because there is no difference from one observation to itself, right? So then the first step is to take the two closest observations and call them a cluster. And then we continue doing that. Take the next two closest points, or the point closest to the existing cluster, and keep doing this and move up in the hierarchy, so to speak, until we reach the opposite of the starting point, where now all the observations form one cluster, a single cluster. And that, of course, is the situation with the maximum within sum of squares. So we go from 0 to the maximum within sum of squares, which is the total sum of squares, when everything is in one cluster. So then everything in between shows us how the within sum of squares increases every time we group observations together in clusters. And as I already mentioned, the two critical parameters, one, and they're obviously related. One is how one defines distance between clusters, and that's the linkage option. So distance between observations is straightforward. Once you group them, how do you compute the distance? That there's a number of different ways of doing this. We'll consider 4 of them. And then once you have decided how you compute distance between clusters, how do you update all the distances to find basically what the next move should be? So how do you update the distances between all the existing points and all the existing clusters and a new cluster? So let's say we take two observations together, they form a cluster. How do we update the distances from everywhere to that cluster, so that then we can again find the minimum distance combination, which is really what it's about? Okay, we'll consider the same toy example as before, and but now we'll group based on the distance matrix between them. This is a distance matrix. It uses Euclidean distance, but it could be any distance metric. So what we're trying to do here is find the two observations that are the closest together. So we're looking in this matrix. It's symmetric, so this is the same. And we find here, for example, that 4 and 5 have the smallest distance between them. So then we're going to group 4 and 5. And they now form a cluster. Now at this point, we need to figure out how we're going to compute the distance between these other points and 4 and 5. And for this illustration, I use what is called single linkage, which is the nearest neighbor distance. So for the distance between yellow and the cluster, it's a distance between yellow and 5. for the distance between pink and a cluster is the distance between pink and 4. That's how it works. So we update all the distances. These distances don't change. The only distances that change are distances to the point 4 and 5. The others are unaffected. So that's a pretty efficient updating mechanism. So as it turns out, 7 is the closest, so we group 7 with 4 and 5. Then at the next stage, and this is all worked out in the lab notes with some detail, we group 1 and 2. At the next stage, we put 3 together with 4, 5, and 7. And then finally, we add 6 to 3, 4, 5, and 7. And every step of this process is visualized in a so-called dendrogram, which is a tree representation of the cluster formation. So we have connections between the observations, I'll show you in a second. And as we move in the implementation in GeoDa from right to left, the within sum of squares increases. I mean, as I mentioned, it starts with 0 and it ends with a total sum of squares, 0 when each observation is its own cluster, TSS when all the observations are one cluster. And so once we have this tree, so this is, I'll show you, this is the tree for our toy example, then we can decide where to cut the tree. So let's see, in our toy example, we started by 4 and 5, which are grouped, and this is the level of the within sum of squares that corresponds to that. And then we group 7 with these two, and then this is the new level of the sum of squares. And then the next step, because of the particular numbers that are in the example, there's a bunch of ties, but basically we see 1 and 2 being grouped together, and then 3 and 7 being added to this group. So if we cut here at the point where we want 2 clusters, we have 1 cluster consisting of these 2 observations, and the other cluster consisting of the remaining 5 observations. That's the notion of a dendrogram. Now, in practice, it looks more like this, and even this is a very small problem. It only has 85 observations, so you can clearly see which is which. And on the left-hand side, we have an example where we cut at 5, and each of the clusters consists of these groupings to the right of the line, and they're highlighted, the observations are highlighted in the color of the cluster. In GeoDa, that also matches the color on the map, on the cluster map. So we see this is one cluster, this is another cluster, this is a third cluster, fourth cluster, and then fifth cluster. And each of these groupings shows us in great detail how the individual observations are grouped together. If we cut more to the right at 8, we have 8 different clusters, 1, 2, 3, 4, 5, 6, 7, and 8. And each time you can see the detailed tree structure, and so what we see is over here very small improvements, actually deteriorations in the within sum of squares, and then once we get to these larger groupings, there are huge jumps in the within sum of squares up to the point here where there's just one cluster, and that is the total sum of squares. So this is the idea. It's in principle is very simple. You group observations together and later clusters together that are the closest from each other, which means that we need to define a distance measure and a way to update the distances as we group things together. But the process of the grouping is visualized in this tree structure, a dendrogram, and then we apply a cut in the dendrogram. So unlike k-means, where we have to pre-specify k, here we can look at the effect of different k's on the clusters by just moving this line around, this cut line around. In GeoDa, this is all interactive, and you can see how the clusters change as you change the cut point. Okay, so what is this good for? It's good for because, especially the reason that I just mentioned, one does not have to pre-specify the number of clusters, or K. A downside is that once you have many observations, let's say thousands of observations, drawing the dendrogram and especially interpreting the dendrogram becomes kind of awkward. It becomes cumbersome. A downside of hierarchical clustering methods, and we'll see this in a few minutes, is that the result is very sensitive to the choice of the linkage function. And some linkage functions are much worse than others. Another drawback, and that is something that we'll consider further later when we look at the spatially constrained clustering methods, is that in a hierarchical clustering method, you get stuck in a given cluster. In contrast, in a partitioning method, observations are reallocated to different clusters, so they can move out of a cluster that they were in, and then later they can move back into that cluster. With hierarchical clustering, it doesn't work that way. Once you're grouped for life, so to speak. You cannot be swapped out of one cluster and into another. So that's a drawback of this method, but it's an important property to keep in mind. So what are these linkage options? And there are several, but we'll consider four the four most common ones. The first one is single linkage, and single linkage is a nearest neighbor criterion. So the distance between 2 points is the minimum distance between them, but the distance between two clusters, A and B, is the nearest neighbor distance. So we take the point in A and the point in B, I in A and J in B, that are the closest together, and that becomes the distance between the two clusters. Then how do we update the distance from any point to a new cluster? So any point P to a new cluster C made by merging A and B. And these update functions, as you see, only need the distances between the points. So it's very efficient in terms of calculation because very few new calculations need to be done. Only the updates of the distances to the particular points that have been merged in a cluster. So that's very efficient. So for obviously the distance from P to the cluster is the nearest neighbor distance, is the distance to the closest point in A or the closest point in B. And then with a little bit of algebra, and this is explained in more detail in the lab notes, this can be expressed as a simple function of the original distances. So 1/2 the sum of the distance between P and A and P and B minus 1/2 the absolute difference between the distance from P to A and the P to B. So this is a difference without a sign, and it's subtracted from this initial half sum. So this is a very straightforward update function. Let's look at what this means in practice. So we already saw 4 and 5 are closest, so 4 and 5 are combined. And now what we need to do is update the distances from all the other ones, 1, 2, 3, 6, and 7, to 4 and 5. And so let's say from 1 to 4 and 5 is the nearest distance, so we take 5. So in the column of 4, 5, we replace it by 5. For 2, it's 447, so we replace it by 447, and so on. So we replace the row, and the column of what the distances are from the other points to 4 and 5, and then we find the shortest distance in this new table. So every time we do one of these clusterings, the table shrinks by 1 row and 1 column, and that, in terms of computation, one can take advantage of this. So in the new table, we see that the smallest distance is between 7 and 4 and 5, and that's exactly what you saw in the figure, which was for single linkage. Single linkage, very easy to implement. However, unfortunately, as it turns out, it yields lousy clusters. The opposite of single linkage is complete linkage. And instead of using nearest neighbor distance, we use the maximum neighbor distance. So the distance between A and B is the distance between the 2 points, one in each cluster, that are the furthest apart. So the maximum neighbor distance. And then similarly, the distance from any point P to the new cluster C made from merging A and B is you look between P and A and find the largest distance, and P and B and find the largest distance and take the maximum of those two. And again, a simple equation is 1/2 of the two distances summed, now plus 1/2 of the absolute difference. And if you don't believe it, you can look at the workbook and see the numerical example, and that actually works out very nicely. So same starting point here, same grouping, but now we look at the largest distance between the points and the new cluster. So we look at and the 2 points that made the cluster. So between 1 and 4 and 1 and 5, now it becomes 583. And 2 and 4 and 2 and 5 becomes 5, and so on. We update the row, the column, and the row, and then we find the smallest number, which there's actually a tie here, 2 and 1, or here 7 and 6, but we don't. In the example that I worked out in the lab notes, we arbitrarily took 2.4, 2 and 1, because that's also how GeoDa implements the ties. It's a random pick. Okay, complete linkage is a little better than single linkage. Average linkage is what it says it is the average of all the interneighbor distances. So instead of taking the smallest between 2 points, one in each cluster, or the largest between 2 points, one in each cluster, we take all of them and take their average. We divide by the number of points in A and the number of points in B. And then the update formula, the update function for a point P to a cluster made from A and B is a weighted average of the distance between P and A and the distance between P and B. So in the distance table, we have these distances already. All we have to do is make the weighted average, and we have the update of the column and row elements in the distance table. In our example, same thing, 4 and 5. So now the distance between 1 and 4 and 5 is the weighted average between 4 and 5. But because the number of points in the cluster is 1 and 2, this is all very straightforward. It's a simple average. But then when they're more complex groupings, NA and NB are no longer 1 or 2, and then it's a truly weighted average. And there's some examples in the worked out example in the notebook. So this is average linkage. And then finally, a little bit different thinking is Ward's linkage, which is, as it turns out, by far the most effective linkage function, but also by far the more complex linkage function. And Ward's method is not based on the simple distances, but on a variance type of notion, is minimizing the variance, so the square difference between the observations in a cluster and the mean from a cluster. Remember, we saw this earlier in k-means. It's a similar criterion. As a result of this, we have to think about these means to compute the distances between two clusters. And for a number of reasons, and actually we saw this in k-means as well, Ward's criterion uses the distances squared, not the distances themselves. So the distance squared between 2 points initially will be 2 times 1 and 1 divided by 1 plus 1. So this goes away, this is 1. And then the mean of a point is itself, so that's the square distance between the 2 points. So initially it's very simple. It's just basically the distances between points. As clusters get formed, it becomes a little more complicated, and with a little bit of algebra you can figure out the update formula for Ward's function. So it's a weighted combination of the square distance from the point to A, the square distance from the point to B, all these are already in the table, and the square distance between A and B, which is also already in the table. And the weights consist of the number of points in A, number of points in the new cluster. This is typically 1, but not always if B is a cluster. And so you update the square distances, again, using nothing but the original data in the table, in the square distance table, and the weights depend on the number of points, the number of observations, actually, that are in each of the respective clusters that are being combined. So the calculations are a little more complicated. Note these are square differences, but still 4 and 5 are the first one, and then the new distances are computed using this weighted average. You can find the specific worked out example in the notebook. So those are the principles. These are the 4 linkage functions. And just to give you an idea of what this means in practice, I again use the Gary example with the same 6 variables and show you the linkage, the hierarchical clustering for the 4 linkage functions. And Ward's linkage is the default because it gives the best result by far. So the result here is 0.482. These are reasonably balanced clusters and look very much similar to the result that we had for k-means. It's not the same, it's definitely different, but it's a similar grouping. And we have the same characteristics, the centers of the clusters, and the sum of squares criteria. Everything is the same as before, and I won't dwell on it. Now, let's look at the dendrogram, which shows the very nicely balanced groupings that we had before. In fact, this is a dendrogram that I've been showing in the previous example. Now we go to single linkage, and right away we notice the existence of several clusters that are singletons. In other words, they consist of themselves, and then everything else is one huge cluster. So this is typical for single linkage, that you keep a number of singletons, and then everything else groups in 1 or 2 very large clusters. So, and the resulting measure of fit is pretty lousy. And often single linkage I find very useful to explain the concept of hierarchical clustering, but not very useful in practice as an actual clustering method. And you see the dendrogram is pretty awful as well. It has, our 4 singletons as a single element, and then everything else grouped in one big cluster. So then average linkage is also pretty lousy, unlike what you might expect. Again, we have a bunch of singletons, these 2, and a few other clusters with very, very small clusters, 5 elements and 2 elements, and then everything else bunched into one large one. Again, the measure of fit is a little bit better than single linkage, but it's still pretty lousy compared to what we had for Ward's, and definitely compared to what we had for k-means. The dendrogram is similarly strange, characterized by a few small clusters and then everything else bunched together. And finally, complete linkage. Complete linkage is closest to Ward's in terms of its properties. This is fairly balanced cluster. There's only one that's a little smaller than the others. The measure of fit is very comparable to Ward's method, and the dendrogram also looks similar to what we had for Ward's method. So hierarchical clustering, especially agglomerative hierarchical clustering, very straightforward. You start with every observation being its own cluster, and you start grouping them that are closest together. The two key factors are how do we compute distances between the clusters and distances between every point and the new cluster, the linkage function and the update function. And we saw 4 different linkage functions: single linkage, nearest distance, complete linkage, maximum distance, average distance is the average, and then Ward's method, which is based on a minimum variance concept and which is by far the best performing hierarchical clustering technique. In the next lecture, we'll look at some more advanced clustering methods. See you then.